Okay, let's talk about the fuel cell charge transport and Ohming laws. This is the schematic illustration of charge transport along a uniform conductor of cross-sectional area A. Cross-sectional area A, length L, and conductivity sigma. A voltage gradient dVdx drives the transport of charge down the conductor. So from the charge transport equation, we can derive this one, and the conductor geometry, we can derive Ohm's law, V equals IR. The resistance of the conductor is dependent on the conductor's geometry and conductivity. So from the relationship, we can define the R as follows, the equation. So when you see the figure in here, the current is start from here and they goes through this direction, right? So because of the voltage, potential is higher in this side than this side, that is the driving force of the charge transport. So the voltage drops means decrease through the transport direction, right? So this part, it has a higher voltage than this voltage. So as we know, we already defined that the J in here, V equals IR. This is the Ohming laws, right? And we already know about this one, J, because we defined in the previous. J equals sigma dV dx, and in this figure it is linear, it has a linear relationship, so V over L. So the voltage is rearranged like this, and this is equals to IR. Okay, from this relation, we can derive the R as follows. So we already know about that the R is proportional to the L and inversely proportional to the A. So remember that. So the friction occurs during this charge transfer process, and this makes the voltage loss of the fuel cell. The friction during the movement. And in a conductor with a cross-sectional area A and length L, as we derived before, the J is expressed like this, right? And V equals to this, following this equation. And in here, V equals IR, and the relationship between charge flux, which is the current density, and current, is I equals JA, right? This is the current density and this is current. So from this equation, we can derive this one, J equals A sigma L in here, and this is IR. So the R equals to L over A sigma. Like that is the meaning of this resistance, right? So if we have the higher conductivity, then the resistance can be reduced. So because of the voltage laws follows Ohm's laws, we call this Ohm's law. So we call this ohmic resistance, or okay, this is not correct one. Ohmic laws, and we define the eta ohmic over potential as follow IR ohmic, and this R ohmic consists of many types of the resistance from originated from the bipolar plate and GDL and catalyst layer and membrane, and also the interconnect part, the contact resistance. So, and from here we can separate each resistance as electrical resistance and ionic resistance. This is two part, and if we sum up these two resistance type, then we get the R ohmic. In the chapter 3, we talked about this figure eta act, which is activation over potential, and now we are talking about the Ohm's laws, and this is the linearly decreased voltage, right? So the voltage of the entire fuel cell increases from the oxidation electrode to the reduction electrode, which is cathode, to give the driving force of charge transfer from the electrolyte. The voltage from the anode to the cathode decreases. So that's why the potential is higher in this side, and this side, cathode side, has a lower voltage. So the voltage drop, if we make a graph for the voltage drop, then the amount of this difference is the ohmic loss. So the figure A is the hypothetical voltage profile of a fuel cell at thermodynamic equilibrium. A is the equilibrium, thermodynamic equilibrium. And the B is the effect of anode and cathode activation loss on the fuel cell voltage profile. And the C is the effect of the ohmic losses on the fuel cell voltage profile. So, although the overall fuel cell voltage increases from the anode to the cathode, the cell voltage must decrease between the anode side of the electrolyte and the cathode side of the electrolyte to provide a driving force for charge transport. And that is the Ohm's laws. Okay, now let's take a look at one example to calculate the Ohm's laws. So there's one example, PMFC. Resistance, find the Ohmic, just Ohm's loss. Okay, we can change it. Ohmic loss of the fuel cell at current density 1 ampere per square centimeter. This is J. Area with 10 square centimeter. And conductivity 0.1 Siemens per centimeter. And the electrical resistance is determined in here. This is the fixed and constant one. Okay, and then we varied the membrane thickness as 100 micrometer and 50 micrometer. So the first case is the 100 micrometer and the second case is 50 micrometer. Okay, to calculate this one, we already know about the R ohmic over potential equals to IR. okay, overall resistance. And as I said, the R is composed of electrical and ionic resistance, okay, and this value is fixed with 0.005 ohm, but this R ionic is dependent on the thickness of the membrane, and also as the current increase, the ohmic overpotential, ohmic loss increase. Okay, so based on this simple equation, we can calculate the ohmic loss. So firstly, let's change the current density to the current. So I equals JA, right? And we already know about that. The current density has the 1. And the area of this fuel cell active area is 10 square centimeter. So we get this one, 10 ampere. This is current. So we inserted this value in here. Okay, then let's calculate the resistance. We already know about the electrical resistance. So okay, depending on the thickness, we can calculate the resistance of each membrane, right? And we already know about the area and length, because the length is the thickness of the membrane, right? And sigma in here. So based on this equation, we can insert each value in here. So 100 micrometer and 100 micrometer, because this conductivity has a unit of Siemens per centimeter. So let's exchange it into the centimeter. So how about the 100 micrometer? What is the 100 micrometer? 1 10 to the 6 meter, then 10 to the 4 meter, and we can convert it into the centimeter. Okay, then now we have 0.01 centimeter. And how about the 50 micrometer case? This is 0.005 centimeter. So if you insert this value into here, L, then we can calculate the ionic resistance in here, 0.01 ohm for 100 micrometer thick membrane, and 0.005 ohm for the 50 micrometer thick membrane. So if you insert this value into here, and the current in here, and finally the electrical resistance is fixed with 0.005, then we get this one. So the ohmic loss is calculated as a 0.15 volt for the 100 micrometer thick membrane, and 0.1 volt for the 50 micrometer thick membrane. So this indicates that as the membrane gets thinner, then the ohmic loss gets reduced. So if the conditions are the same, the largest the ohmic loss decreases as the film, the membrane, is made thinner. Okay, then the charge transfer linearly decrease the operating voltage as the current increase, as we talked about. Okay, linearly decreases operating voltage. Okay, as the current increases. So the resistance depends on geometrical shape, as we learned. Geometrical shape. What is the geometric? Length and area in here. And fuel cell resistance is proportional to the it's not proportional. The resistance is inversely proportional. Inversely proportional. So that is why we should use the area specific resistance, which value is independent on the area of the membrane, right? So the area specific resistance, okay, we will talk about later. And fuel cell resistance is proportional to the thickness, okay, inversely proportional to the area and proportional to the thickness, as thin as possible in fuel cell electrode. That is why we should get the thinner membrane. And resistance load, ohmic loss, losses occurring in other parts of the fuel cell are summed in series. Okay, this is very important thing. Okay, we sum up all the resistance. Okay, so because the electrical pathway is constituted in series. Okay, in series is very important. An ion electrolyte element dominates the fuel cell resistance. as we see in the previous example, the ion electrolyte is very important for the ohmic resistance. So this is the plot for the ohmic loss, IR. So if we increase the I, okay, this current, then the ohmic loss gets larger. And also, if we have the larger R ohmic, then the slope is more steep. Okay, this is the way of the increasing of the R ohmic. So the effect of ohmic loss on fuel cell performance. This is the graph for it. And charge transport resistance contributes a linear decrease. Linear decrease in fuel cell operating voltage as determined by Ohm's law. The magnitude of this loss is determined by the size of R ohmic. So as we talked before, the fuel cell resistance inversely proportional to the area, right? So there we should use the area specific resistance. And we express the current as the current density because of the comparison based on the unit area, right? And how about the resistance loss? We also should use the standardized resistance value for normal area, unit area. So we use the area specific resistance, which is ASR. And the unit of this ASR is ohm square centimeter, ohm square centimeter. So in the fuel cell, we use the ASR from now on. So using ASR, the resistance, the ohmic loss is calculated from the current density. Okay. Ohmic loss. So if we match the unit of this equation, ampere per square centimeter is the current density for the current density, and for the ASR, ohm square centimeter, then this is same with the volt. Okay, So the total ASR is calculated by multiplying the fuel cell resistance by area. Considering the original definition of equation for resistance, it is necessary to find the resistance independent of the area, because the resistance is inversely proportional to the area, as we talked before. Okay, then R, as we learned, A sigma L, and what is the ASR? ASR is AR. Okay, if you multiply A into the left and right side, AR, this is the ASR, and the ASR defined as L over sigma. This is the ASR. So let's take a look at one example for calculating the ASR and ohming loss. So when the current density is 1 ampere per square centimeter, find the voltage loss, ohming loss of the two fuel cells. There is no fuel cell. Okay, fuel cell number 1, FC number 1, is very small sized fuel cell, small size, and the area of this one, A1, equals to 1 square centimeter, and R 0.1 ohm. And for the second fuel cell, the membrane and electrode assembly has the area of 10 square centimeter, is bigger than that, and it has the resistance, overall resistance is 0.02. Okay, so when we check this resistance, right, this resistance, the fuel cell number 1 has a higher resistance, right? So we can think that this fuel cell number 1 has a higher ohmic loss. Okay, but actually let's calculate from based on the ASR with the two ways. So firstly, the ASR, to calculate the ohmic loss, right? To calculate ohmic loss, we multiply the current density and the ASR together, J ASR. Okay, following this, the current density is 1 ampere per square centimeter. So if you insert this in here, and we should get the ASR for each fuel cell. So ASR number 1, ASR number 2 is expressed like this. And for the fuel cell number 1, it has the area of 1 square centimeter. So this is the ASR for the fuel cell number 1, and the fuel cell number 2 has the 0.02 ohm, and it has the active area of 10 square centimeter. So it has the 0.2 ohm square centimeter. This is the ASR. So if you insert this value, 0.1, 0.2 in here, then for the fuel cell number 1, we have 0.1 volt. And for the second fuel cell, we have 0.2 volt. Okay, because we thought that the fuel cell number 1 has a higher resistance, right, than this one, but actually the ohmic loss is higher for the fuel cell number 2. because of this area effect, right? In the same condition of the current density is very important concept in here. So we should take account of the area into for the evaluation each fuel cell system. And the solution number 2, the other way to solve this one is based on the Ohming loss equals to IR. Right? In this case, the I is the current, not a current density. So if you exchange the current density by into the current by multiplying the area of each cell, I1 has lower lower I current, right? Then by the 10 times. And if you insert this I into the I in here, then we get 0.1 volt for the first one and 0.2 volt for the second fuel cell. So anyway, the results are the same, and because of we use the current density usually in the fuel cell, then we should use the ASR. Okay? Or you can exchange the current density into the I. Because of this I is larger for the second case, that is why the Ohming loss is higher for the second case. Okay, as we learned the standardizing ASR, the ASR is defined as resistance times area of the cell, and it equals to L over sigma. So the shorter the length of the conductor, the smaller resistance surely. And if we compare the ion conductivity and electron conductivity, this one, ion conductivity over electron conductivity equals to about 10 to the minus 6, then that means this electron conductivity is much higher than the ion conductivity. So that is why we need to minimize the electrolyte resistance. And there is a practical problems in making electrolytes thin. The first one is mechanical strength, right? The breakage, make the short circuit or the out of order of the fuel cell, and inhomogeneity, thickness, constant weakness, and the roughness is very important when we make the fuel cell membrane. And the electrical short circuit, when the thickness of the electrolyte and the roughness, okay, thickness and roughness of the electrode are similar. Similar, then it is very important to make it as a low roughness surface. And the other one is fuel cell permeation. The reactant permeation. In this case, usually we use the hydrogen crossover or the oxygen crossover. The permeation is the same word with this crossover. So in the anode, the H2 hydrogen gas is crossover to the cathode, and this makes the hydrogen peroxide, and from these chemical species, it is very highly detectable chemical species, so it degrades it degrades the membrane surface or the electrode, which means the dissolution of the PT catalyst or the electrode surface or the Nafion ionomer network in here. So this hydrogen crossover or oxygen crossover is very critical issue for assuring the durability of the fuel cell. So that is why nowadays people use the ceria or the other materials for reducing these attacks, chemical attack. That is the core that is called radical scavenger. And the other thing is contact resistance. Contact resistance is also should be considered, and insulation breakdown, because there is a voltage difference if the size of the gap, the insulation, because the electrolyte is an insulation layer, right? And the insulation gets thinner, then the insulation breakdown can occur. Okay, let's read it together. The total electrical resistance of fuel cell is the sum of the resistance. As we learned, this is considered in series, generated by each of the different components. An electrical interconnection, anode, cathode catalyst layer, cathode catalyst layer, and electrolyte. This is the one of the components, right? And contact resistance between various layers of the fuel cell. The channel electrode contact resistance, or GDL, right? In this, the channel means that bipolar plate or flow channel. And experimentally difficult to distinguish all resistance losses from various sources. Okay, so if we measure of this A and B and C, and we consider the resistance is the sum up of this one, but actual resistance always is higher than each component, because there is always a contact resistance between these layers. So it is difficult to reflect the total resistance by experimentally measuring the resistance of each component of the fuel cell. So it's difficult to reflect total resistance by measuring each component. So, and also difficulty in evaluating the fuel cell performance due to these factors. Okay, even though we know about the resistance each component, and there we cannot exactly anticipate the effect of each resistance on the fuel cell performance, right? So it's strongly needed for in situ performance evaluation of the fuel cell. The in situ measurement is required. So what is in situ? In situ means during operation. Okay, so we construct the fuel cell overall, and we should operate, and during the operation we should check the each component resistance. The reverse word is ex situ. And the largest resistance loss in fuel cell is the electrolyte. Okay, if we see this figure, it is very simplified figure, and this is the catalyst layer, And as we learned, there is a GDL, gas diffusion layer, and this is the bipolar plate. Bipolar plate, and on the bipolar plate there is a flow channel, right? Or the flow channel. Okay, this is the schematic illustration, and for the anode, the composition is the same with the cathode. Okay, in this case, there is a R interconnect, and R cathode, R electrolyte, R anode, R interconnect. So these each resistance should be summed up for evaluation of the total resistance. If there is a membrane in here, and the catalyst layer, and the GDL, and the bipolar plate, then we just think about it. This electrolyte resistance and catalyst resistance, GDL resistance, and bipolar plate resistance. But at the interface of all these interfaces, there is the contact resistance, R contact. So we should consider about this one too. And also the contact resistance is dependent on the pressure, okay, the compression pressure. So also we assemble the fuel cell. During the fuel cell, the torque for the assembly of this single cell is very important factor too. And stack, when it comes to stack assembly, and that is one of the most important thing to operate, and removing the gas leakage outside. So the total ohmic resistance presented by a fuel cell is actually a combination of the resistances. Combination. Okay, is given by the total fuel cell resistance is given by the series sum of individual resistance components. Okay, then let's check this one. The ionic or the electric. This is we talked about the electrical resistance in offside, and now we talk about the electrolyte resistance, ionic resistance. The best electrolyte ion conductivity in fuel cell, the best one, it has a 0.1 Siemens per centimeter. In here, the ohm to the -1 is same with the Siemens. This is a Siemens, okay? Remember that. This is the unit for expressing the conductivity of the charge for the charge transport, and we use the Siemens. Okay, so that is the Siemens 0.1 Siemens per square per centimeter. So in very thin electrolytes with a 50 micrometer membrane, it has the ASR of 0.05 ohm square centimeter. And 50 micrometer porous carbon fiber electrode, carbon cloth. That is not electrode, just the GDL. It means the GDL. The ASR is smaller than 5 times 10 to the -6. Okay, so that means the ASR is very highly different, and the ohmic the electrolyte has very higher higher ASR than the GDL. So well-designed fuel cell overall ASR is about 0. In the ranging in 0.05 to the 0.1 ohm square centimeter. And the electrolyte resistance is largely occupied, and if it is difficult to reduce the thickness of the electrolyte, finding a high ion conductor, right? If there is a thickness limit, then you should find out the high ion conductivity material is an alternative, and it is difficult to develop the satisfactory ion conductor. The main electrolyte types is divided by water soluble and polymer and ceramic electrolyte. Yeah, so of these, the material property and the transport property are very different. So how can we calculate the conductivity each of the species? Firstly, the physical meaning of this conductivity is quantifies the ability to flow electric charge under an electric field, a measure of how well a substance accepts charge transfer. The conductivity of a material is affected by two main factors. Okay, the first one is number of carriers required for charge transfer and transporter's mobility, the mobility in the material. And we denote the number of carriers as the concentration, right? C. And the mobility, from now on, we use the U. Then the conductivity, remember that this is the conductivity, is proportional to the C and U. And in front of that we multiply ZF in here. So in here, Ci is the charge carrier molar concentration, and Ui is charge carrier mobility. And this is the carrier's charge number and Faraday constant. Okay. The differences in nature of electrons and ions cause differences in electron and ion conduction methods. Okay, there is a figure 4.8. Let's see these together. Okay, in here, that is the illustration of charge transport mechanism. For the first figure, A is the electron transport. Okay, this is the electrode, right? Then, okay, this is the electrode, and this is the electrolyte. This is for ion, and this is the electron. In a free electron matter, the valence electrons detach from the immobile metal atom. Immobile metal atom is M+ in here, core, and move freely in the response to the applied field. So we call this one electrode C, right? Electron C. So it can move through this one, this metal into the metal freely, and their velocity is limited by the scattering from the lattice. Okay, the lattice means because they are scattered, electron is scattered like this one, so the velocity, mobility is dependent on this scattering effect. And second one is a charge transport, ion transport. In this crystalline ionic conductor is accomplished by a mobile ion, which hope is this one. Hope. This is the jumping, okay, to the other side. Hope from position to the position within the lattice. The hopping process only occurs where lattice defects such as vacancy, okay, vacancy or interstitials are present. Okay, in here there is very important vector because the C plus should be immobilized. They cannot move because they made a chain by themselves, so they are fixed in that position, and only the anion A minus can move freely in this crystal. So if there is a vacancy in here, they hop to this side. Okay, that is one of the mechanism of the ion transfer. And also they can go through the between the ions. So we call this one interstitial, and we call this one hopping. Okay, there is two ways for the transport of ion, hopping and interstitial. And the C plus should be fixed, and the A minus can move freely. But it is not exactly fully when we compare the electron in the electrode, right? Okay, then this is the electron conductivity in a metal. How can we calculate the electron conductivity based on the equation, specific equation with the mobility? So for simple conductors such as metal, the Drude model, this is the Drude model, shows the mobility of free electron is limited by scattering, the acoustic protons, lattice defect, or impurity. This scattering is due to this factor, and free electron mobility is expressed as like this, and tau in here, tau is the mean free time between the scattering occurrence, and m is the mass of electrons, we already know about this value, and q is the basic electron charge, we already know about this too. So the tau is the variable in here. What this means is tau, if there is an electron in here and there is a crystal lattice in here, the metal ion, and the electron is bumped into this metal, and they are scattered in here and they go through this way. This time, okay, the bumping time the time between this bumping or scattering is the tau. So if it is coarse in the coarse lattice, then it has the higher time, mean free time, than this one. So that means mobility is proportional to the mean free time, and q and inversely proportional to the mass. So this equation is made. And if you insert the u into the sigma, the conductivity, then we can know about this one. sigma is expressed through based on this following this equation, and substituting for the obtained electron mobility into this equation, then we can calculate the general conductivity of metal. The value is ranging in 10 to 6 to the 10 to the 8 Siemens per meter. So it is the conductivity of the electron in a metal. Okay, then let's talk about the ionic conductivity of crystalline solid electrolyte. The ion mobility depends on the hopping speed from one position in the grid to another position, and this is the hopping speed, and this hopping speed is dependent on the diffusion, right? So diffusivity is the constant for is proportional to the conductivity, and the conductivity the conductivity is proportional to this diffusivity, and this diffusivity is defined as like this. This is the how often to try the hopping process, and this is the activation barrier for the hopping process, and R is the gas content and T is the temperature. And this is the diffusivity depending on the other three factors: temperature and activation barrier, and the how often to try the hopping process. And the overall mobility of the ions in the solid electrolyte is then defined as this equation. So this D is inserted to here, ZIFD over RT, and in here, as we know, ZI is the number of charges of ions and F is the Faraday constant. Okay, then if you insert this U into the conductivity equation, then we can get this final expression for the conductivity, concentration, diffusivity, and the other things, and also the temperature. So ion diffusivity in liquid electrolyte is generally has the value of 10 to the minus 8 meter square per sec, and diffusion of polymer electrolyte ions, this is the diffusivity, D has almost the same value with the liquid electrolyte. How it happens, we will check it later in the next slide. Next 3 slides. So the diffusion degree of and also the diffusion degree of the ceramic electrolyte at about 10,000 degrees Celsius, they have 10 to the minus 11. So the difference between them is about 1,000 between the polymer electrolyte and the solid ceramic electrolyte. So the typical ion carrier concentration, surely in the liquid electrolyte, the concentration C is higher and the highest in the liquid electrolyte, ranging from 10 to the 3 and 10 to the 4 mole per cubic meter. And the polymer electrolyte, they have in this range, and the ceramic has the comparable value that of the polymer electrolyte. And if you substitute these values into the conductivity equation, then now we have the value between the 10 to the minus 4 to the 10 to the minus 2 Siemens per meter. And if we okay, then maybe I think this is the polymer. This is for the polymer and this is for the ceramic. And the focus of this research in fuel cells is the development of the better electrolytes. And because the electron conductivity for the electron, the conductivity is about in the range of this. So actually we can know that the conductivity of electron is highly larger than the ions. And as we discussed, there are three main electrolyte materials available for the fuel cell, which is water soluble and polymer and ceramic. So the characteristic of the fuel cell electrolyte, this is a requirement, right? High ion conductivity and low electrical conductivity, and high stability in oxidizing and reducing atmosphere, and low fuel crossover. And in the case of the solid, it requires moderate mechanical strength, not that brittle, and it should have the high tensile stress, and elongation to breakage also an important factor, mechanical property for the electrolyte membrane, and the convenience of the production and low cost too. An ionic liquid is a liquid itself and at the same time an ionic substance. Sodium chloride dissolved in water, and this exists in the water as an ion form. This is water soluble because this is the water soluble material. And if we increase the temperature of the substance and apply the heat to the sodium chloride, then it will be melt, right? So molten, it would be molten. So it exists and in the form of ion, and it has also the conductivity by itself because this is the liquid itself. So all water-soluble liquid electrolyte fuel cells use the matrix material. We already talked about this one. That immobilize, fix, that make the liquid fix or support them. And the matrix performs the following loads. The matrix means there is solid substrate and we dipped. There exists a liquid form in this matrix. So the role of this one is providing the mechanical strength, right? Mechanical strength, and minimize minimize the distance between the electrode while preventing the electrical short, preventing the short circuit, and prevention of the permeation of the reactant through the electrolyte. If there is a vacant in here, then the gas can penetrate from the anode to the cathode. If there is an unsupported liquid electrolyte, then it is severely permeated to the gas, reactant gas, and the fuel cell cannot operate if the pressure is not balanced or at high temperature. What this means is, if there is a pressure in the cathode, and if there is a pressure in the anode, and if the cathode pressure is higher than the anode, then this liquid leak to the porous material in this anode side, and it goes out, and there would be a vacancy in here. So use of the very thin electrolyte with this matrix, 100 micrometer, from the 100 micrometer to the 1 millimeter, to compensate for mechanical strength and the permeation problem together. For the AFC, alkaline fuel cell, the use of concentrated water-soluble potassium hydroxide, KOH, and phosphoric acid fuel cell, PAFC. In here, in this fuel cell, we use the concentrated phosphoric acid, H3PO4, and so this is the charged ion, which is moved from the anode to the cathode. Or the pure phosphoric acid, okay, aqueous solution or pure acid, phosphoric acid. And MCFC, molten carbonate fuel cell, the use of molten potassium or lithium and carbonate ion in here, and fixed to the matrix support, and this material is molten. Because if the temperature goes over 450 degrees Celsius, then it is molten, right? So we use it as a electrolyte directly. And ion conductivity in aqueous or liquid environment, approach to driving force. The driving force over friction balance model to explain the ion conductivity of this one. In the aqueous and liquid environment, so ion in liquid, the driving force, electrical acceleration, and the resistance is the friction of the drag resistance. The final velocity is determined in the equilibrium of these two forces. So when you think about it, if there is a lane drop, it goes down, further down, due to the gravity. But actually, as this value, the V, the velocity goes over to critical value, then these two drag force, the drag force and driving force, is in the equilibrium state, and the velocity is determined. So this is the same phenomenon of this one. In the liquid form or aqueous form, what is the driving force of it? The driving force is the electrical force. And the voltage, this is the voltage gradient, and Ni is the number of charges of ions, and Q is the basic electron charge. And as a resistance, the drag force is derived from Stokes' law, because this is the liquid form, right? So we consider about the fluid mechanics to this one. So the drag force is determined by 6 pi mu r v. The Fd, drag force, is proportional to the viscosity, and the particle, as the particle size gets larger, then drag force will be increased, and the velocity too. So to make this equalize into the equation, then we use this term. Then what is the mobility in this aqueous or liquid form? The mobility U can be determined by making the two forces equal. And mobility is defined as the ratio between the applied electric field and the resulting of the ion velocity. So V over dV dx is the definition of the mobility in this case. So if you make these two equations as same, then we can derive this equation for determination for the mobility. So mobility is determined by the size of the ion R and the viscosity mu here, because the others can be considered as a constant, but actually there is two variables in here, viscosity and the ion size of the ion diameter. In the table 4.2 in the textbook shows the mobility of various ions in aqueous solution. So when you found out the specific species, the mobility in the table, and if you insert the mobility into to calculate the conductivity, then we can get it. So the proton H plus is hydrated by water molecule. So the number of protons, number of hydrated water molecules, that means the H plus proton is not solely moved through the ion channel. They combine with the water molecule, and they form this oxonium ion, and in this form they move through the anode to the cathode and membrane. So for the confirmation of the conductivity, finally we get this one. So if you substitute the ionic mobility values in table 4.2 into this equation, the ionic conductivity of the aqueous electrolyte can be calculated. And this table, the value in this table is accurate in low dilute aqueous solution. If it is in the high ion concentration, then the strong electrical interaction with ions, because they have a repulsion force between them, right? This makes it difficult to calculate the conductivity. And the value obtained from the actual conductivity is lower at high concentration. So if you find, remember this mobility is in the assumption of the low dilute aqueous solution. And this proton, the oxonium ion, the mobility is very high in this table. And hydroxide ion, also the mobility is very high. So this is U, only U, not a conductivity sigma. This is U. So if you insert this value into here, then we can get, and while considering the concentration effect, then we can calculate this one directly. Okay, then let's take a look at the example in this chapter 4.3. The question is find the conductivity of 1 mole. Okay, this is not the correct one. In the textbook, 0.1 mole potassium hydroxide aqueous solution. Okay, this is the question, and let's solve this one. And as we see in the previous slide, the sigma is defined as, sigma I is defined as Zi, the charge number, Faraday constant, and concentration and mobility. And this is the aqueous solution, so that's why we can use this this equation. And firstly, let's find out, okay, if this material is in the aqueous state, then there is a potassium ion and hydroxide ion. And let's check the mobility for each. Okay, there is a potassium ion, so we can find out the mobility of this. And also hydroxide ion is like this. So now we can find the UI for each species. And what is the concentration then? The concentration of each species is a 0.1 mole and 0.1 mole per liter. But actually, the unit of the mobility has the centimeter scale, so we should exchange in this in the unit of centimeter, right? In here. So for the potassium ion, we can use the 0.1 mole per liter, and 1 liter over 1,000 cubic centimeter. Then we can get this concentration in the centimeter scale. And also same with the hydroxide ion. When you substitute the mobility in table 4.2, then already we can find this one. This one, and square centimeter, and also square centimeter. Then already we know about the charge number, because this has, each species have the 1, right? 1 as a charge number, and there is a Faraday constant in here, and this is the concentration C, and only difference is this one, mobility. So if you take it into this equation, then we can get the conductivity of each species. In here, the conductivity for the hydroxide ion is somehow higher than the potassium ion. So if you sum up these two values, these two values, then we can get the total conductivity. So this is the result of it. So finally, we can find the conductivity of 0.1 mole potassium hydroxide aqueous solution like this. And actually, the conductivity of this one will be lower than this value because actual value is lower because we assume in the table, assume the mobility is in the low dilute aqueous solution. It is comparatively has higher concentration. So that is the reason of the occurrence of the error. And the conductivity is more dependent on high mobility of ions. Okay, then let's take a look at for the polymer electrolyte. This is for the polymer electrolyte. Okay, let's rewrite this one. Sigma 0 EA KT. So in this case, what is the effect of the temperature? So in this equation, the temperature term is in here. So when we rewrite this one, T R. So if we increase the temperature of this one, this is decrease, increase. So overall, this part is increased. So if we increase the temperature, then the conductivity will be increased. So temperature increase, conductivity increase exponentially. Then polymer is a good ion conductor. There is a two function to make a function of this polymer as an electrolyte. There should be the fixed charge site. The fixed charge point is the opposite charge to the moving ion. Okay, this is a fixed charge point. If they have minus, then the moving ion should have the plus. The transient center that accept or emit moving ion, and also in the polymer electrolyte there is a very important factor, the presence of a free volume, which is open space. The free volume, open space. So this improve the ability of ions move through the polymers like a liquid. This is a solid, but it acts like a liquid. So because of this free volume, polymer free volume mechanism, we call this one as a vehicle mechanism. It is different from the hopping mechanism. So vehicle mechanism make possible this polymer electrolyte has a very high conductivity. So any free species, the vehicle species, the high conductivity due to the free volume. Because of this free volume, the water molecules move through the free volume of the polymer membrane. And the naphthalene, which is sulfonated polytetrafluoroethylene, PTFE. The PTFE is the backbone of the naphthalene CF chain. There are so many CF chain. It is the Teflon. There is Teflon-like base. So we use this one. Okay, let's see the figure together. This is the schematic of ion transport between polymer chain, and polymer segment can move or vibrate in the free volume. This is important, free volume, thus inducing physical transfer of ions from one charged site to another. So they have a minus charge, the fixed charge site, right? This is the fixed charge site, and because of the free volume, they can extract or contract or release. So if there is a presence of the plus charged ion in here, which is H plus, and in the Nafion case, this is the SO3 minus sulfonic acid. So they attract first in here H plus, and they contract, and it in this left side chain they emit the proton to the light side. So through this mechanism it can move through here, and without this they drive. If there is a water channel, they can driving mechanism. Oxonium ion can move through this water channel. This is a driving mechanism. The ion transfer in polymer electrolyte. Okay, this is the form of the Nafion. The Nafion contains sulfonic acid. This sulfonic acid is SO3 minus, and this is the chain chemical composition of the Nafion, and there is a formation. The backbone is generally composed with the CF. This is Teflon, PTFE, and in the side chain, at the end of the chain, there is a sulfonic acid, which acts as a fixed charge ion site, and this is a moving ion. So this provides this is charged fixed branch for proton transfer. And the Teflon, they have the Teflon base. The Teflon is very hydrophobic, right? Which hate the water, right? And they act as a retraction. It makes it easy to the water remove from the surface. And also they provide mechanical stiffness, and also the most important thing is the chemical stability is very important. Chemical stability too. And separation from the water, the proton exists in as a oxonium ion and sulfonic acid side chain. Transfer of aqueous solution state. This means there is a channel of this fixed charge one, and this acts as a channel, water channel. So this oxonium ion in here, they move through this channel with the interaction of the fixed charge site. There is an explanation. PTFE is this one. So this is the principle for the proton transfer in the polymer electrolyte. The Nafion free volume is the small pores connected to each other by nano-sized pore. Nafion free volume is small pores. This is the free volume, and the Nafion's wall is surrounded by the functional group. This one, I mean this red line is filled with the SO3 minus sulfonic acid. In the pore, the oxonium ion is formed. and separated from the side chain. Okay, from this one, they combine together and they generate the oxonium ion. And sufficient water presence in the case the oxonium ion aqueous solution state transfer. The ion conduction is similar to the conduction in aqueous electrolyte. So that is why the polymer electrolyte has very high conductivity than others. And it accelerates the movement of water by repulsion of the Teflon-based PTFE, right? The hydrophobic material. In the original, the phobic means in the Greece, hate, and hydrophilic means love. So if the surface has love the water, then we call it hydrophilic. And if the material hydrophobic, with the hydrophobic, they hate the water. So this acts as a repulsion force for it. And the proton conductivity in the nafium polymer electrolyte is the same as that of water-soluble electrolyte. So when fully hydrated, in the state of the fully hydration, then the membrane has very high conductivity.